So good afternoon to all of you. So on behalf of Guru Nanak Institution's Technical Campus, I welcome you all for this faculty development program on classical optimization techniques in manufacturing systems. So just for the current session, we are going to discuss on multivariable optimization methods with constraints. The main emphasis of this session is to demonstrate solvation of multivariable optimization problems using MATLAB. So what is the solver that is available from the MATLAB, and then how to make use of that solver in solving multivariable optimization problems with the constraints. Just before proceeding with the discussion on various techniques of solving multivariable optimization problems with constraints, so just by reiterating the importance of optimization in manufacturing domains. So just as we all know, so when the beauty of the optimization can be realized, so when there is abundant amount of resources in terms of manpower, in terms of raw material, and in terms of capital, with respect to each and every resources, if there is no limitation, then as much as we want to produce, we can go ahead. But under that unlimited amount of resources, there is no guarantee that the productivity can be obtained. The profit making can be, there is no guarantee that the profits can be generated. But however, so when there is a limitation in terms of capital, in terms of manpower, and in terms of all other resources, then under such scarce resources, how best the output result can be produced. So under that limited number of resources, the beauty of the optimization can be realized. So in such a way, so the optimization can be defined as the process of minimizing the undesirable factors and then the process of maximizing the desirable aspects. So especially in manufacturing scenario, so cost of production is the undesirable factor. So that is why that must be minimized. So if you take profit generation, so it could be a desirable factor. So that is why it must be maximized. So in such a way, minimization of undesirable aspects and maximization of desirable aspects is nothing but the process of an optimization. And then if we take in case of aerospace industry, so while constructing the aircraft, so weight factor is the undesirable. That is why weight of the aircraft must be minimized. So minimization of the weight of the aircraft, so that is a undesirable factor. Then efficiency maximization is said to be desirable factor. So in such a way, so in each and every field of engineering, we have to minimize the undesirable aspects, and then we have to maximize the desirable aspects. And then as we have been using several number of optimization techniques, or n number of optimization techniques nowadays, so they are not the overnight result. So with the contribution of so many authors from the last few decades have been, so many number of techniques have been developed. So as it is demonstrated in the current slide, so they are all the different contributors developed different types of optimization techniques in one or the other way. So such a way, from the last few decades onwards, so several optimization techniques have been developed, and nowadays we have been getting the fruitful advantage of those techniques in solving realistic problems. And then once again reiterating the importance of optimization, just while designing the aircraft. So when the aircraft is not optimized, and when the aircraft design is optimized, then what is the difference that can be clearly perspective, right? So when the aircraft design is not optimized, the effect of solar radiation on the passenger will be more. When the aircraft design is optimized, the effect of solar radiation is said to be very, very minimal. So similarly, in another system design, if you observe, so while designing the power transmission system, so if the system is said to be designed optimized, then what is the power loss to inefficiency? And if the system is not optimized, what is the power loss to inefficiency and other cost of energy and energy usage? So all such things are clearly perspective between the optimized power transmission system and unoptimized power transmission system. So such a way, as a teaching faculty, we all know that nowadays in pure design engineering, what is the level of scope for research? That we all know. So almost all got saturated. Similarly, in thermal engineering field also, in pure thermal engineering field, so if you see the level of scope for research, there is almost all got saturated. So if at all there is any such scope, so that is only towards optimization by means of adding the flavor of optimization in all engineering domains. So the scope for research can be enhanced, and that too nowadays because of stiff competition in each and every manufacturing industry. So unless otherwise the consumption of resources and the consumption of capital and all other resources are optimized, then only the competition can be in the stiff competition, any industry can be surveyed, and then for years together the business survival can be made possible. So such a way, so nowadays because of ever changing scenario everywhere, so the beauty of the optimization is said to be very well realized, and then we all know what is the advantage of or fruitful advantage of usage of using optimization techniques in various aspects. So irrespective of engineering field, in all domains, so with equal degree of importance, so the role of optimization has become inevitable nowadays. So that is the known information to all as a teaching faculty. And further in civil engineering field, so generally if you see the reservoir construction, while constructing the reservoir, so storage capacity must be maximized. That is a desirable factor. So maximization of the storage capacity, and then cost of construction must be made. That is undesirable factor. So in such a way, in each and every engineering field with equal degree of importance, the role of optimization is said to be most important, and it has been widely under usage. So further in any manufacturing industry, especially for the production planning and control department. So as we know that the PPC department is like a heart of, like a human heart for any industry. So unless the PPC department functions very well, the overall prosperity of the industry cannot be made possible. So that is why in each and every aspect of production planning and control of various activities of any manufacturing industry, the role of optimization plays the crucial role. And then so from the current slides, so in various different domains of engineering, so what are the various dimensions in which the optimization can be, or the optimization plays the crucial role. So in certain aspects for efficiency maximization, in certain aspects for cost minimization, in certain aspects for weight minimization. So in such a way, in different perspectives, so the optimization plays the crucial role. So just by analyzing this simple example, so we can realize the beauty of the optimization. So here there is a limited amount of sheet metal, so its size is only 20 by 20. So from this sheet metal, so we have to prepare a container. So how best the volume can be maximized. So that is why, since we don't know the dimensions, only this square shape of the sheet metal is available. So from that available size of the sheet metal, so on each of the 4 sides, so some amount of material must be removed. So since we don't know the dimension, so simply that dimension can be denoted as x. So on each of the 4 sides to the size of x by x, the material can be removed, and then the edges can be folded, so that the container can be made. So from that after folding the edges, so if we estimate the, or if we develop the expression, mathematical expression for volume of the container, so that is so length, width, height. So such a way, for any realistic problem, so we need to develop the mathematical expression, and then upon solvation of that mathematical expression with a suitable type of optimization technique, so we'll be able to get the result. So as we all know, so as far as the optimization process is concerned, so for to the extent of 70 to 80%, so most of the industrial problems from small scale industries to large scale industries, 80% of the problems can be simply solvable by classical optimization techniques itself. even in research perspective also, if something is mathematical modeling oriented, so we need to develop the expression, and then we need to prove whether the expression being developed is said to be convex or concave. So that way, by deriving appropriate proofs, so we can prove the convexity of the expression or concavity of the expression, so that such a way the mathematical modeling can be developed, and then its optimality can be proved by using appropriate criteria. So that is the expected thing by every journal publisher. So that way, most of the research problems can be simply solved by classical optimization techniques itself. So that is why, irrespective of the field of the engineering domain or irrespective of the engineering specialization, so nowadays, so it has become mandatory for all, so to have some minimal knowledge in the field of optimization, and what are the various optimization techniques, and what are the various circumstances under that each and every type of technique can be used. So such a way we can realize the beauty of the optimization in each and every aspects of manufacturing scenario or business scenario. So as we know that as far as optimization, general statement of the optimization problem is concerned, so we have to find out the solution. So generally the solution can be expressed as design vector capital X, so that is in terms of x1, x2 and so on xn, so which can minimize or maximize the function f of x subjected to some inequality constraints and equality constraints, right? So if the problem is if the constraints are there, there is a constraint optimization problem. If there is no any kind of constraint, that is said to be unconstrained optimization problem. So now just will discuss a few methods which are mainly meant for solving multivariable optimization problems with constraints, and then for just 20 to 25 minutes we will explore a few things, and then I will demonstrate how to solve so all that problems irrespective of the methodology or algorithm being specified in SSRAW. So just by using simple MATLAB solver, how to solve all the multivariable optimization problems subjected to constraints. Just if you see what are the various methods that are available to solve multivariable optimization problems subjected to constraints. So just here, so from SSRAW, if you see, so with respect to the nature of the constraint, with respect to the given nature of the constraints, so the suitable technique can be adopted, right? So if you see a multivariable optimization problem subjected to equality constraints, when the objective function is there, and then on the given constraints are set to be only equality type constraints. So under such scenario, so generally these are all the three different methods which are generally under usage. Solution by the method of Lagrange multipliers, then solution by direct substitution, solution by the method of constraint variation. Out of all these methods, so most popularly people have been using solution by the method of Lagrange multipliers, right? So if anyone asks any question about optimization, so they may ask something about Lagrange multipliers method, right? So just one simple example, if you see, so from the current example, so the objective function f of x is given, and then the constraint, the given constraint is said to be equality type constraint. So just before from that given objective function and then given constraint, so we need to formulate the Lagrangian function. So while formulating the Lagrangian function, so gx is equal to 0. That means right hand side constant must be moved towards left hand side, or otherwise the left hand side variables can be moved towards right hand side. So most familiarly better to move right hand side constant towards left hand side, so that x1 plus 2x2 square minus 3 equal to 0. So such a way, so g of x is equal to 0. So such a way we have to convert that given equality type constraint before formulating the Lagrangian function. So just after manipulating the given constraint, so in the form of gx is equal to 0, then we need to formulate the Lagrangian function. So that is f of x plus lambda g of x. right? If only one constraint is there, so lambda 1 g1x. If two constraints are there, lambda 2 g2x, plus if three constraints are there, so lambda 1 g1x plus lambda 2 g2x plus lambda 3 g3x, and so on, lambda m gmx for m number of constraints. Such a way the Lagrangian function can be continued like that. So then from that, for any, while solving any problem with respect to this multivariable optimization problem subjected to equality constraints, right? We need to find out the develop necessary conditions, and then we need to develop sufficient conditions. From the necessary conditions, we have to find out the solution by trial and error method, and then from the sufficient condition, we can prove that whether the solution is said to be relative minimum or relative maximum. If the solution is relative minimum, then the objective function is a convex in nature. If the solution is a relative maximum, then the objective function is said to be concave in nature, right? So such a way we can prove the convexity or concavity of an optimization problem. So here, as part of that, the necessary conditions are nothing but the first order derivatives. So with respect to each and every variable, so we have to carry the first order derivative of the Lagrangian function, and it is equated to 0. And then as far as this current example is concerned, so the first three equations with respect to x1, x2 and lambda, the first order derivative is carried out, and then that are equated to 0. Then upon solvation of these three equations by trial and error method, then we can find out the solution, that is design vector x, which is in terms of small x1 and small x2, optimal values of small x1 and small x2, and then Lagrangian multiplier value lambda, that is also obtained. Then again, to prove the optimality of this, whether this solution is relative minimum or relative maximum, right? So for that purpose, we have to develop the sufficient conditions. So just the root of the polynomial equation can be determined from the following determinantal equation. So here, in terms of z, for the n number of variables and m number of constraints, right? So this is the determinantal equation from which we can find out the root of the polynomial z. If the root of the polynomial z is positive, if the z value is positive, then the solution is said to be relative minimum, and then the expression is said to be convex in nature. If the z value is negative, the solution is said to be relative maximum, then the expression is said to be concave in nature. So such a way, from this determinantal equation, the root of the polynomial can be determined, and then whether that root of the polynomial is positive or negative, based on that we can decide the nature of the solution, whether could it be relative minimum or relative maximum. So such a way, this is the for n number of variables and m number of constraints. So this is the general determinantal equation from which the root of the polynomial z can be determined. But whereas in our current example, there are only two variables and only one constraint. So that is why, so it can be from this general expression, we can rewrite the determinantal equation as L11 minus z. So as it is demonstrated in this current slide, so this is the way how you can write down the determinantal expression. So L11 means, so dou square L by dou x1 square, then L22 means dou square L by dou x2 square, then L12 equal to L21 equal to dou square L by dou x1 dou x2 or dou square L by dou x2 dou x1. So both will be same. So such a way, L11, L12, L22 and L21, all these three things, L12 is equal to L21, L11, L22, those things can be determined. And then here G11, G12, G11 means, so only if you see the subscript 1112, G11, subscript 11, so that 11 represents, so first x only one constraint, first constraint with respect to first variable partial derivative. So that is dou G1 by dou x1. So first subs out of 1, the first one represents the constraint number, and then second one represents the order of derivative. So whether could it be with respect to variable 1 or variable 2. So G11 means, so first constraint with respect to variable 1, then G12 means first constraint with respect to variable 2, only one constraint here we have. So and then these two things are to be written in vertical manner, whereas diagonal element must be 0. So from this, if you find out the determinant, so in terms of z, we can get the polynomial expression. So from that, if you find out the z value, there is a negative value. So since z is negative, the solution whatever that we got, so that is x star equal to x1 star, x2 star. So that solution is said to be relative maximum, since z is negative, right? So and then the objective function value is said to be maximum, relative maximum. So such a way the expression is said to be a concave in nature. So such a way, so when the multivariable optimization problem is subjected to equality constraints, so we can use the method of Lagrange multipliers method, right? So objective function subjected to equality type constraints. So Lagrangian multipliers method can be used. So then further, if you say multivariable optimization problem subjected to inequality constraints, without equality, only if inequality constraints are there. So in such case, the method of Kantakar conditions can be used, right? So only when the given problem is subjected to inequality constraints without any equality constraints, only inequality. So if inequality may be less than or equal type or greater than or equal type. So in such case, here again, if combination of both less than or equal to and greater than or equal to type is there. So in such case, you have to, with respect to the given objective function, so you can manipulate all the constraints either in the form of less than or equal to type or greater than or equal to type only. So with the mix up of both less than or equal type and greater than or equal to type cannot be solved, right? So that is why we have to convert it. Yeah, please. Anything? The constraints must be converted into less than or equal to type or greater than or equal to type. So let us say in the current example, so problem is minimization type, and then constraints are set to be less than, inequality constraints are set to be less than or equal to type. So in such case, so the Kantakar conditions will play the role of sufficiency condition as well as necessary condition as well as sufficient condition. The Kantakar conditions, whatever that we derive from the given problem, will play the role of necessary conditions and then sufficient conditions. The solution can be determined as well as the optimality can be decided, right? So in such a way, for this given combination, minimization type and less than or equal to type constraints. So once the problem is given, here also we need to convert the we need to convert constrained optimization problem into unconstrained optimization problem. That is a Lagrange multipliers in the form of Lagrangian function. We need to formulate the problem. So once the Lagrangian function is formulated with the given constraints, then with respect to each variable x1, x2, x3, right? So one Kantakar condition, that is dou f by dou xi plus sigma j equal to 1 to m lambda j dou j by dou xi is equal to 0. With respect to each and every variable, so the first order derivative of the Lagrangian function, that is one Kantakar condition. Then again another Kantakar condition, lambda j gj is equal to 0. So with respect to for each constraint, for each given constraint, we have to multiply with Lagrangian multiplier, that is lambda 1, lambda 2, lambda 3, depending upon the m number of constraints, right? So if only one constraint is there, lambda 1 g1x, if 2 are there, lambda 1 g2x, if 3 are there, lambda 3 multiplied with g3x. So like that, with respect to second Kantakar condition, we have to derive the expressions. Then again, third Kantakar condition, that is nothing but simply the given inequality constraint, constraints only. So that is gx less than or equal to 0 with respect to m number of constraints. Then again, here one thing we have to remember that, so problem is minimization type and then given constraints are less than or equal to type. So here lambda j must be greater than or equal to 0. So for if the problem is minimization type, in that case, the first two Kantakar conditions are common for all 4 possible cases, right? Whereas the last 2 will be changed. So for minimization type problem, if the constraints are less than or equal type, then lambda j should be greater than or equal to 0. If the constraints are greater than or equal to 0, then lambda j must be less than or equal to 0, right? If the problem is minimization type, so these two, the sign of these two conditions will be opposite to each other, right? So minimization type problem, so gjx and then lambda j, so these two inequality sign will be different. So that is two cases, right? Here one case, if it is greater than or equal to 0, another case is minimization greater than or equal to type constraints. So in that case, lambda j will be less than or equal to 0. The first two will be same, the first two will be remain same, and then third one is a given constraints, and then fourth one is Lagrangian multipliers. The sign of inequality sign of that Lagrange multipliers is opposite to the given nature of constraints, right? That is two cases. So less than or equal type, greater than or equal type. And then if the problem is maximization type, in such case, if the constraints are less than or equal to type, then lambda j is also said to be less than or equal type. If the constraints are greater than or equal to type, then lambda j also is said to be greater than or equal to 0, right? Both the sign, the inequality sign of both will be remain same. So such a way here we may have the scope for 4 possible different cases, right? So just a simple from this given exercise problem from SS Rao, right? So there is an agreement to supply 50 refrigerators at the end of each month, that is for the end of first month, second month and third month, and then the cost of production of each refrigerator, X refrigerators, is also given, and then the carrying cost is also given. So from this to optimize the total cost of production and carrying, so what is the optimal quantity of refrigerators to be produced during the first month and second month and third month, right? So total cost is nothing but a sum of the summation of total production cost and holding cost. Then production cost with respect to each month is given, and then carrying cost is also given. So whatever the stock that is left during the first month, so that will be carry forward to the second month, and then again at the end of the second month, so whatever the excess quantity that is remains left, so that can be carry forwarded to the third month. So such a way the carrying cost is set to be incurred during the second month and third month, right? So such a way carrying cost, production cost for 3 months, and then carrying cost for the second month and the carrying cost for the third month, so that the total expression can be obtained, and then the constraints can be the problem objective function is being formulated, and then constraints are developed here. So from this by using Tucker conditions, so as here the given constraints are greater than or equal to type, and then objective function is said to be a minimization type. So for all these types of problems, so these are all the 4 Tucker conditions. With respect to first one, so we need to, that is a dou f by dou xi plus lambda 1 dou g1 by dou xi plus lambda 2 dou g2 by dou xi plus lambda 3 dou g3 by dou x, with respect to each variable, right? With respect to each variable, with respect to x1, x2, x3, so 3 expressions. With respect to first Tucker condition, so we may derive 3 expressions, and then lambda j, that is the second Tucker condition. With respect to that, again 3 expressions can be obtained. Then with respect to third Tucker condition, so again 3 inequality expressions can be obtained. Then with respect to fourth Tucker condition, with respect to fourth Tucker condition, so again 3 inequalities can be expressed, right? So such a way now by solving, so this Tucker with respect to each Tucker condition, 3 expressions are to be derived with the help of E1 to E6. With the help of E1 to E6, by trial and error way, we can find out the solution, and then whether that solution satisfies all these E7 to E12, right? So if each of that solution satisfies all these E7 to E12, that becomes optimal solution. Otherwise, if any one of these constraints, that is E7 to E12, if any one of the constraint is violated with respect to the so-called solution being determined, then that solution is not said to be optimal, right? So such a way here, by using the Kantakar conditions, so the method of Kantakar conditions, the Kantakar conditions can be derived, and then the solution can be determined by using the trial and error method, and then that solution can be verified with respect to certain inequality conditions, so that the optimality can be decided. So in such a way, when the problem is subjected to only inequality type constraints, so in such case, the method of Kantakar conditions can be used. So equality type Lagrangian multipliers method and inequality type Kantakar conditions, method of Kantakar conditions. Then further we may have geometric programming problem. So here also, if you see the nature of the geometric programming problem, the objective function is expressed in terms of polynomial, and constraints are also said to be expressed in terms of polynomial. So polynomial is nothing but the power functions of the type. So generally, in most of the design engineering perspective, so the objective function is nothing but the sum of several cost components. So such a way, f of x is sum of the several cost components like u1 plus u2 plus and so on un. So where each cost component is expressed as power functions of the type, that is ci x1 power a1i, x2 power a2i, and so on xn power ani. So that way the polynomial can be defined. That means the objective function is non-linear, which is said to be in the polynomial form, as well as the constraints are also said to be in the form of polynomial, which is a non-linear in nature. So generally, geometric programming has some unique feature. In almost all optimization techniques, first we will find out the solution of the variables, and then after that, from the solution of the variables, we can find out the solution of the objective function. So unlike all optimization techniques, in geometric programming problem, we can find out the solution of the objective function first. From the solution of the objective function, we can find out the solution of the variables. So that is the unique feature of the geometric programming approach. So generally, in most of the design engineering problems, the application of geometric programming problem is said to be mostly under usage, right? So even though if the problem is not said to be in polynomial form, so we can manipulate the problem in the form of polynomial, and then we can use the geometric programming approach specifically. So if one wants to solve the problem using geometric programming approach, right? So such a way, coefficient will be there, coefficient of the component, and then a variable 1, variable 2, variable 3, and so on, nth variable, right? So and then a1i, that is exponent of variable 1, exponent of a2i, exponent of variable 2, and so on, ani, exponent of variable nth variable, exponent of nth variable, right? So here a1i, a2i, ani. So that means in ith function for a1i means in ith function for variable 1 exponent, in ith function variable 2 exponent, in ith function for nth variable exponent. So such a way, the exponents are to be rewritten, and as per the methodology, we can solve the problem using geometric programming approach. Further, specifically, so some problems can be expressed, the objective function of some problems can be expressed in terms of second order polynomial form. If the objective function is in second order polynomial form, then we can use the quadratic programming approach. In previous case, objective function is non-linear, and then constraints are also said to be non-linear, right? So they may be equality or inequality type. So whereas here in this case, quadratic programming, when the quadratic programming approach can be used. So in this case, the objective function is said to be second order polynomial form, and then constraints are said to be linear in nature. Objective function is a non-linear, and the constraints are said to be linear, both inequality and equality type. So here in this case, as per the methodology demonstrated here, so here only inequality constraints are considered, linear inequality constraints. If the greater than or equal to type constraints are there, so in such case we have to convert that greater than or equal to type constraints into less than or equal to type constraints, and then we can solve the problem using this methodology, right? So such a way here the design vector x in terms of decision variables x1, x2 and so on xn, then c is nothing but a coefficients of the variables in the objective function, that is the coefficient of x1, x2 and so on xn. So that is a vector. C is a vector representing the coefficients of the variables in the objective function. Then b is a vector representing the right hand side constants of the linear inequality constraints. So here only one constraint, that is b1. If two constraints are there, b1, b2, and like that if m constraints are there, b1, b2, b3 and so on, m number of constraints. So that is b is a vector representing the right hand side constant values of the linear inequality constraints. Then again capital A. So this is a matrix representing the left hand side coefficients of the variables of linear inequality constraints. So a11, a12 and so on, a11, a1n. So for up to n number of variables, so in first constraint a1, a2, a3 and so on n coefficients. Then again in second constraint, second constraint is there, then that is so a21, a22, a23 and so on, a2n. Then like that if for mth constraint am1, am2 and so on, amn for n number of variables. So that is a matrix representing the left hand side coefficients of the variables of linear inequality constraints. Then D is a again matrix representing the coefficients of the squared variables in the objective function. That is coefficients of x1 square, x2 square, x3 square and so on, xn square, and then x1, x2, x2, x3, then x1, x3. So that are the coefficients. That is matrix. D is a matrix representing the coefficients of squared variables as well as multiplied components. So now to solve the problem, so just one simple example here I will demonstrate. So here one objective function is given, and then the constraint is linear inequality constraint is given. So that should be represented in matrix form. So this is a 4,6, that is vector C. So then again x1, x2, that is a design vector. So here x transpose. Then this is matrix D, right? Matrix D. So here, so this one is x1 square coefficient, this one is x2 square coefficient. So this is x1, x2 coefficient divided by 2, and this also x1, x2 coefficient divided by 2. So then the given constraint is also said to be expressed in matrix form. So and then from that here the Kanteker conditions. So from this, if you develop the Kanteker conditions in this matrix form, so that Kanteker conditions will play the role of necessary conditions and the sufficient conditions. So from this Kanteker conditions, so all the vectors and matrices in this Kanteker conditions, we need to substitute all the vectors and matrices. Then after substituting all the vectors and matrices in this Kanteker conditions, so this is the matrix form we will get. From that we have to develop the linear equality equations. From that linear equality equations, again we have to verify the basic feasibility of the solution. So once the basic feasibility of the solution is verified, then artificially we need to develop another objective function in terms of artificial variables. So again by means of substituting out that artificial variables, then we will get the artificial objective function, that is in terms of small w, and then with the help of this linear equality constraints and then a new objective function, so we can formulate the initial basic table, and then this table can be solved using simplex method like a linear programming model. The way how we solve the given LPP problem using simplex method, with the same simplex method, if you solve this problem, finally we will be reaching to the final optimal solution of the variables, and then whatever the solution of that new objective function w we got, so by substituting the solution of that variables in the given original objective function, we will get the solution of the original objective function, right? That means the solution of the artificial objective function is nothing but the solution of the original objective function. So that way the quadratic programming approach can be used when the given objective function is said to be second order polynomial, and then constraints are said to be linear in nature. Apart from this, so as it is demonstrated in the current case, so these are all the various methods which are generally used to solve multivariable optimization problems subjected to constraints, right? So generally search methods from initially we have to give some random initial guess. From that initial guess, so by means of using heuristic approach or random approach, finally we will be able to reach the final optimal solution. So these are all the various methods. Just have an idea of these methods, and then again here under direct methods, what are the various different techniques that are available. Under indirect methods, what are the various different techniques that are available. Here penalty function methods are most frequently under usage. So interior penalty function method, exterior penalty function method. So in both the interior and the exterior penalty function methods, right? So we need to formulate one auxiliary unconstrained objective function, right? So in case of interior penalty function method, so with respect to the given objective function constraints, we need to formulate auxiliary unconstrained objective function. So from that auxiliary unconstrained objective function, then we can derive the necessary conditions by solving the solution by trial and error way. Then we can find out the final converged solution, right? So in case of interior penalty function method, so the value of the penalty parameter can be varied from some reasonably high value to very low value at some fixed interval, so that in that process we'll be able to observe the convergence of the solution. So after once the solution gets converged, then easily we may able to decide so what is the optimal value of variables, and then optimal value of auxiliary unconstrained objective function, and then what is the optimal value of the given original objective function. So when r tends to 0, almost all the solution gets converged. That is interior penalty function method. Then in case of exterior penalty function method, so similarly the problem is to be converted into auxiliary unconstrained optimization problem from the given objective function constraints. So there again from the trial and error way, by carrying first as part of developing the necessary conditions, first order derivative is to be carried out. From that the variables are to be expressed in terms of penalty parameter. So in this case, when the r value tends to infinite, when the value of the penalty parameter tends to infinite, the solution gets converged. So for that purpose, so from reasonably lower value to higher value, that means up to infinite, the value of the penalty parameter can be simply varied at some fixed interval, so that the convergence process can be observed, so that at the end, after carrying few iterations, then what is the value to which the solution is going to get converged. Easily we can identify that converged solution, right? So such a way, with respect to the specific nature of the given constraints, so what is the suitable type of technique to be adopted, right? So traditional manually, if at all we want to solve using traditional optimization techniques, so that way we need to have the knowledge of solving all these optimization techniques and with the theoretical knowledge of these techniques, so any problem whatever being developed or whatever the mathematical model being developed, that can be the nature of the constraints in that model can be analyzed with respect to the nature of the constraints. What is the suitable type of technique can be adopted, so that we can decide, right? So irrespective of all these methods, but in MATLAB, so we have provisions, or we are several solvers have been developed to solve all these optimization problems irrespective of the constraint. Irrespective of all the methods, whatever that we learn or whatever that we study in SSRAW as part of engineering optimization techniques, so irrespective of those methods, so just if you are familiar with this solver, there is a fmin_con. So any kind of problem can be simply solved by using this solver, simply by developing one M file for objective function and then one M file for constraints in non-linear constraints. For linear constraints, we need not to develop the M file. Directly we can input the data. Whereas for non-linear constraints, we have to write another M file, and then finally another M file to run the objective function constraints, right? So such a way, totally 3 M files we have to write: one run file, one M file for objective function, and one M file for constraints. So just here the fmin_con, so by virtue of its nature, so it stands for solving the minimization type problem only, minimization type problem. So if we have the maximization type problem, so in such case what we have to do, that we have to convert the maximization type problem into minimization type problem, and then by using the same MATLAB approach, by using the same solver, we can solve. Only the difference is in the output solution, so we will get the negative sign for the objective function. So irrespective of that negative sign, simply we can consider the numerical value. So such a way, the same solver can be used to find out the solutions of maximization type problems also, right? If maximization type problem is given, we have to convert it into minimization type problem. So conversion is, so simply by multiplying it with the negative sign. If the maximization problem is multiplied with the negative sign, it will be converted into minimization type, so that we can make use of the same solver. So here this solver handles all these types of constraints. So first one is non-linear inequality constraints. So that constraints must be less than or equal to type only. If greater than or equal to type constraints are there, so we have to convert them into less than or equal to type, right? And the right hand side must be 0 only. If any constant is there on the right hand side, that we have to move it towards the left hand side by multiplying it with the appropriate sign, right? Then first one, non-linear inequality constraints. Then second one is non-linear equality constraints. Non-linear equality constraints. Right hand side must be 0. Then third one is linear inequality type constraints. Linear inequality type constraints, right? Ax less than or equal to b. Linear inequality type constraints. So if greater than or equal to type is there, so we have to convert it into less than or equal to type, right? And the constant must be on the right hand side. Then fourth one is said to be linear equality type constraints. Linear equality type constraint. So such a way, with the help of using this same solver, so all these 4 constraints can be handled while determining the solution by writing appropriate run file in a suitable manner, right? And then this for each variable, lower bound and upper bound, lower bounds and upper bounds with respect to each variable that we have to define, right? So generally, if you are working in a purchase department, so based upon the previous experience, we may be able to tell what is the maximum demand for which the orders can be placed, or what is the minimum demand for which the orders can be placed, or if you are working as a boiler operator, so easily we may be able to tell what is the maximum pressure and what is the minimum pressure, so that may happen during the working condition of the plant, right? So based on the experience, field of experience, easily one may be able to specify the lower bounds and upper bounds. So all these whatever the constraints that are given, So the given constraints are said to be strictly manipulated in this particular format only, in this particular format. Now, the syntax for this fmincon, minimization of constrained optimization problems, right? So this is nothing but, so these are output arguments. So that is a x value, that is it specifies values of various decision variables, unknown variables. Then a fval, so it specifies the value of the objective function. And then exit flag. So what is the termination condition, on what basis, so how the algorithm has been terminated, right? So whether the solution under the solution is executed, so what is the termination criteria, or on what condition, under what circumstances the program has been terminated. Then output information regarding the output solution. So few more information can be displayed in the output in the command, right, in the command window. Then lambda is a Lagrangian multipliers values. If at all we want to display Lagrangian multipliers values, so this output argument we have to provide. Then gradient value, that is the first order derivative value, that is a slope. So if you want to display gradient values, we have to specify this output argument. Then Hessian, that is a second order derivative value, second order partial derivative values. So if you want to specify, demonstrate that values, we have to give this output argument. So in general, so we need only x values and f values. So if you put only x and f, so in the output window only we will get x values and f values. So if we put all these things, then apart from x values and f values, so all this information can be displayed. So but mostly we want, for the decision making purpose, we want only x values and objective function values, right? Then these are the input arguments. These are the input arguments. In the same order, we have to give all the input arguments. It is easy to remember also. It is easy to remember. So here function represents, that is nothing but we have to recall the m file of the objective function. Fun represents, so m file of the objective function, and then x0 represents initial guess that we have to provide. Whatever the initial guess that we give, that is the, it is a vector, initial guess is a vector. Then a comma b, so a comma b, aeq beq. So a is a matrix representing the left hand side coefficients of the variables of linear inequality constraints, Then b is a vector representing the right hand side constant values of the linear inequality constraints, right? Then AEQ, again it is a matrix representing the left hand side coefficients of the variables of linear equality constraints, Then BEQ is nothing but a vector representing the right hand side constants of the linear equality constraints. Then a lower bound, so it is a, again vector, and upper bound again it is a vector, then a non-linear constraint. So this is the, again we have whatever the m file that you wrote regarding the non-linear constraints, that m file we have to recall here. So here this m file is related to the non-linear constraints. Then this function Fn, that is nothing but a m file, recalling m file for the objective function. Then finally options. So through optimset, options can be executed. So if you want to see the iterative by iterative result, so in such case through optimset you can specify the options, right? So order is first m file for objective function, then initial guess, then matrix representing the left hand side coefficients of the linear inequality constraints, then B is a vector representing the right hand side constant values of the linear inequality constraints, then again AEQ, matrix related to the left hand side coefficients of the linear equality constraints, then BEQ, vector representing the right hand side values of the linear equality constraints, right? Lower bound, upper bound, then again m file for the constraints, then options. So that way output arguments and then fminCon, then input arguments. So that way we have to write the m file. So before writing run file, with respect to this syntax, we have to write the m file for objective function, m file for constraints, and then one run file, right? So just here, for the sake of your information, so exit flag. So in terms of some integer values, both positive and negative, if it displays 1, so what is the information it indicates? If it displays 0, what is the information it indicates? If it displays -1, -2, right? And 2, 3. So these are all the various integer values, positive and negative integer values, in terms of which the output exit flag information can be specified, right? So only the thing is, so if it is 1, then that only executable solution. So other than 1, so all other things indicate that the solution is not executed due to some error in one or the other way. Then gradient, second order, first order derivative values. Then gradient, Hessian, second order partial derivative values. Then Lagrangian multipliers values. Then again output function. So these are all the various information generally we can find out from the output argument called the term output, right? So just by taking one simple problem, so we'll see how this fminCon can be worked out to solve multivariable optimization problems subjected to constraints. So irrespective of the type of technique, right? For all types of problems, we can make use of this solver, right? Even if the problem is unconstrained, the same problem, unconstrained problem also can be solved using fminCon. So in such case, regarding this constraints, so we have to put empty square brackets only, This is this example is again from the SS Rao only. So design of open rectangular box, which is given from geometry programming approach, right? So how we can solve the same problem subjected to this constraint, with constraints and without constraints. So here again, the open rectangular construction of the open rectangular design and manufacturing of the open rectangular box, right? So that is the main intention. So to maximize the volume, so what are the optimal values of design parameters? So what is the optimal value of length, width and height? The cost of the material on each of the sides is given. So cost per square meter on bottom side of the sheet per square meter is given. Cost of the bottom side sheet, cost of the sheet on sides per square meter, cost of the sheet at the ends per square meter. There is also. Then again here. So here the intention is the total volume of the grain to be transported 80 meter cube, and for each round trip the cost incurred, that is also given. So that is why here the total objective function to be expressed as a cost expression, so that by minimizing that cost expression, the values of the decision parameters can be optimized, right? So cost of the box plus the cost of the transportation. So such a way, total area of the bottom side, total area of the sides, total area of the ends we have to find out, and then per square meter cost with respect to each side is given, so that total cost of all sides we can find out, and then cost of transportation. So total volume of the grain to be transported 80 meter cube. So per trip, how much volume of the grain can be transported? That is equal to the volume of the box. So volume of the box is so x1, so length, width, height, x1, x2, x3. So that number of trips, total volume of the grain by volume of the box. So that total number of trips we can find out, and then per trip cost. So that total cost for all trips we can find out. So such a way the cost expression is developed. So here there is no constraints are here. So this problem is said to be unconstrained optimization problem. Whereas for the same problem, if the little bit modification is done, so minimize the cost of constructing the open rectangular box subjected to the constraint that a maximum of 10 trips only are allowed for transporting the 80 meter cube of grain. So here the constraint is, so only 10 trips are allowed, only 10 trips. So there is a constraint. So objective function is so cost of the box, whereas the constraint is number of trips, right? So this for this problem, if we develop the M file for objective function, and M file for nonlinear constraints, nonlinear inequality and nonlinear equality constraints, and then run file we have to develop, right? So is it visible, my dear colleagues?
Yes sir, yes sir.
So M file for objective function. So this is a function, F function. This is a built-in word only. So in MATLAB, the same we should not replace any other function. We have to type function, then F. So F represents the objective function. We can use F or any notation we can use to represent the objective function. We can use F, we can use Z, or we can use any other notation. But whatever the notation that we use here, the same notation should be used here, right? And then simply we have to type the objective function here, right? So that is a M file for the objective function, right? Any difficulty here? So this is a file name in terms of variables X. So this file name we can keep based on our own interest. We can keep any file name, right? I can keep Nagaraju within brackets X, or RAM X. So file name is our own interest. So this is the file name, so which is decided on our own, right? Then here this notation F, this also any notation can be used, but here and there, so same notation should be used. And then we have to type the objective function simply. So and then at the end semicolon, right? So this is the way how we can write the M file for objective function. Any difficulty here, my dear students? So it is simple one, right? So then again another M file for the constraints, that is non-linear. For non-linear constraints only we have to write M file. Non-linear inequality and equality type constraints, we have to write the M file, right? Again function, then space within brackets, within square brackets, C space CEQ. C represents non-linear inequality constraints, then CEQ represents so non-linear equality constraints, and again this is a file name. So we can specify file name, right? That is in terms of X only. So and then continuously here in our problem only one constraint. So that is 80 by x1, x2, x3 less than or equal to 10. That is 8 by x1, x2, x3 less than or equal to 1. So there is the only one inequality constraint, non-linear inequality constraint. So if two constraints are there, within the square bracket, so constraint 1 separated by semicolon, then constraint 2. If 3 are there, so constraint 1 separated by semicolon, constraint 2 separated by semicolon, constraint 3, like that within the square brackets. So all the constraints can be simply typed, right? And then CEQ, non-linear equality type constraints. So in our in the current problem, so we don't have any non-linear equality type constraints, only inequality type constraints. So that is why it is simply empty square bracket only, right? And then run file for this, as per the syntax F min con. So first clear all CLC. So just to clear the command window during each and every iteration. So these two generally, as we know, we can write. And then initial guess, so we have to give. So generally how initial guess can be provided. So based upon our field of experience, we may able to specify the lower bound and upper bound, right? So with respect to the lower bound and upper bound, So randomly we can provide the initial guess, predict initial guessed solution. So here, since the lower bound is, so since the author knows the solution for this problem, so the lower bound is specified as 0, 0 for all three variables. Then upper bound is specified as 20, 20, 20. Then in between that, so any value you can provide for x1, x2, x3 as initial guess, right? So initial guess, lower bound, upper bound, that we have to specify. Then again, here in the current problem, for this problem, we don't have any linear inequality equations, right? We don't have any linear inequality equations. Similarly, we don't have any linear equality type equations. So that is why, so A is empty square bracket, B is empty square bracket. So these two are related to linear inequality type. Then these two are represents, so linear equality type matrix, and since these two are not there, no linear inequality and equality, simply we can put empty square brackets for all these four things. That is a matrix A and a matrix AEQ, vector B and vector BUQ. Then options, so optim set. So optim set is the solver again to execute the options. So display within a single inverted quotation, then iteration by iteration result. Then algorithm, that also, if you don't want all this algorithm, what is the nature of algorithm being adopted by optimization the MATLAB, then simply we can put up to display iter, right? So if you know the algorithm, we can specify, otherwise we can simply delete this. We can simply delete these things, right? So then here in output arguments, so I want only x values and f value, design vector, there is the values of the decision variables and the value of the objective function. Then solver, so this is a recalling m file for objective function at the rate of gpp underscore main, right? Then initial guess, then a b, here simply here, since we have specified here a is declared, b is declared, AQ is declared, BQ is declared. So simply we can write, or we can put empty square, nothing wrong. So even we can write AQ, BQ here, right? So since all these things are declared initially, so that way simply as per the general syntax, we can write all the input arguments continuously. Before that, we have to declare each and every input argument here, whatever that is applicable. Then this is lower bound, upper bound, lower bound and upper bound. Then again, this is a constraint. This is a constraint representing the M file, representing the nonlinear constraints. Then at the end, options, right? And then again at the end, to execute the values of the nonlinear inequality and equality constraints, right? So this C comma C space CEQ within square brackets, so that file name, so that the values of that constraints can be executed, right? So this is the way we can write M file for all the problems. So just wait a minute so that I can demonstrate the M file. Similarly, for other things also I will demonstrate the M file, MATLAB files. So just as already we discussed, so this is the M file for objective function, right? So here, while saving the file in MATLAB, so whatever the file name that we gave, so with the same file name we have to save it, that we have to remember. So GPP X, so with that same, so actually this is so GPP mains are actually this is, so with the same file name we have to save it, right? Whatever the file name, GPP underscore main, GPP underscore main. So that is the M file for the objective function, and then M file for the constraints. So here only we have nonlinear inequality type constraint, so that is specified, whereas a nonlinear equality type constraint is not applicable, so that is specified as empty square bracket. Then another file is run file. So we have to declare all necessary input arguments before writing the syntax, output arguments and input arguments. There is initial guess, lower bound, upper bound, then a matrix A, vector B, matrix AEQ, vector BEQ, then options, So all these things. Now if we execute it, so if we run it, so we can find out the solution in the output window, right? Command window. So there is x value, so x1 value, x2 value, x3 value, then objective function value, then value of the nonlinear inequality constraint, right? E power minus 10, that is 10 power minus 9 multiplied with 10, the value, this value multiplied with 10 power minus 9, that is e power minus 09 means 10 power minus 9, right? So this way we can solve the problem. Another problem, so whether this file is visible, my dear colleagues?
Yes,
Yes,
sir.
sir.
Heat exchanger problem. So here again the same exercise is taken from the SS Rao, right? So objective function is given and then subject to the set of the constraints, then followed by all the bounds, lower bound and upper bound. So up to 8 variables. So xi is up to I equal to 4, 5 and so on 8. So this constraint is for variables 4, 5, 6, 7 and 8, right? x1 lower bound upper bound, x2 lower bound upper bound, x3 lower bound and upper bound. So that is the given problem from the same textbook itself. So here m file for the objective function. So this is the file name I gave. So same objective function. Then again another m file for nonlinear constraints, right? So constraint 1, this is a colon dot dot dot. So to specify the continuation only. So in the same line, instead of typing all the constraints, so just by putting the dot dot dot, that represents the continuation of the same command prompt, right? Continuation of the same syntax. And then again CU key is empty square bracket. So here another m file for nonlinear inequality constraints. Then again another run file is written, run file. So here we have both the linear inequality constraints, but we don't have linear equality constraints from the given problem, right? So here from the first constraint, we will get the linear inequality constraints, and again from second one also we will get linear inequality constraint. So from this with further simplification we will get linear inequality constraint, whereas G4 is a non-linear, here x1 x6 multiplication. So this is a non-linear, then G5 is non-linear, then G6 is non-linear. These three are non-linear, but whereas G1, G2, G3 that are so linear inequality constraints. So with the further simplification we can specify the values of the variables and right hand side constants, right? So from that m file for objective function, another m file for non-linear inequality constraints, 3 constraints. Then here initial guess. Since the author knows the solution, based upon the solution, the initial guess is given here. In between lower bound and upper bound, so some solution value you can give, right? Initial guess we can give. So such a way, even other than that, it is no mandatory to give the initial guess between lower bound and upper bound. Any initial guess you can give, that is not a mandatory. So then again A is a matrix representing the left hand side coefficients of the variables of linear inequality constraints. Here totally how many variables are there? So 1, 2, 3, 4, 5, 6, 7, 8, for 8 variables and 3 constraints. So that way 3 rows, 8 columns, 3 rows, 8 columns. So if you want to type in the same line, we have to separate by semicolon, or otherwise in the matrix form we can give, right? So x1 coefficient, x2 coefficient, x3 coefficient, x4 coefficient, x5 coefficient, x6 coefficient, x7, x8 in the first constraint, then coefficients of all 8 variables in the second constraint, then coefficients of all 8 variables in the third constraint, right? Then lower right hand side constants vector, that is a B, lower bound, upper bound, then options, then syntax, right? So output arguments x values and f values, then f min con. So objective function for m file for objective function, then initial guess, AB matrix and vector related to linear inequality constraints. Then these two things are empty square bracket, which are not applicable here. That is linear equality constraints, matrix vector, then lower bound, upper bound, then again another M file, recalling M file of non-linear inequality constraints, then options, right? So if we see the MATLAB files for this, so my dear colleagues, whether the files are visible, heat exchanger, right? Hello, my dear colleagues.
Visible, sir.
Yeah. So heat exchanger objective function, M file for the heat exchanger objective function. There is M file for objective function. Then again regarding the heat exchanger problem, so another M file for the non-linear inequality constraints, non-linear inequality constraints. Then again another run file, So if we run it, we will get the solution for this. So this is the solution of all 8 variables, x1, x2, x3, x4, x5, x6, x7, x8, then objective function value, and then values of the 3 nonlinear inequality constraints. Here actually the value is not 0 here. So in the run file, I gave format bank. There is only after decimal point up to 2 digits only it displays, right? So that is why the values are, that means here the values are very, very minor only. This is not 0, this is not 0, value is there. So since I gave that format bank option, so that is why it is executed, value of the nonlinear inequality constraints, right? So then again another gate train problem, if you see. So here for a gate train objective function, M file for the objective function. So same from the SSRAW textbook itself, the same problem is taken. So M file for objective function, and again another M file representing the nonlinear inequality constraints. Here also we don't have a nonlinear equality constraint. That is why it is empty square bracket, right? And then finally a run file. So here in this problem we have linear inequality constraints. So that file I will share Word file I will share you. So here if we run this M file, we will get the solution of this gate train problem. Here total variables 1, 2, 3, 4, 5, 6, 7, 7 variables. Solution of all the decision variables and the value of the objective function, right? So this is the output information regarding the number of iterations, then algorithm used, all these things. Then solution is successfully executed and terminated. Then Lagrange multipliers values in the form of matrix form. Only up to that only in the output argument it is given, right? So this is the solution for the gate train problem. Then again another simple example, one simple example I will show you. So example 2. So this is the for the given objective function m file. Then again this is for the given nonlinear inequality constraints, another m file, and this is the run file with respect to the given problem. So then simply if you execute it, so in the command window, we will be able to find out the solution. x1, x2 value, x2 value, and objective function value apart from other information, right? So this is the way how we can write m file for objective functions and m file for nonlinear constraints, both nonlinear equality and inequality, and another one is run file. All these 3 files we have to write, and then we have to solve irrespective of all the methods for all the 4 types of constraints. So this solver fminCon can be executed, right? So just in today morning in the first session, so sir was explaining about genetic algorithm, right? So in general, the same problem we can using GA to solve the genetic algorithm, to solve the problem using genetic algorithm, right? The MATLAB solver is GA. So using GA solver also we can solve the same problem. So just I will demonstrate one problem, but regarding the input arguments, slightly it changes. So just let me open that file. So my dear colleagues, whether the current file is visible, my dear colleagues, PDF file, right?
Yes, sir.
GA file. So here also same solver is GA. So only the thing is we have to provide the input arguments in a right manner. So in output arguments, so just generally we are desired with x values and objective function value, x and f value. So exit flag, that information and all redundant, right? So that, but we have to provide all input arguments in a particular sequence only. So first we have to write the m file for the objective function. There is a fitness function. We have to recall at the rate name of the m file of objective function. Then number of variables we have to specify here. Number of variables. Then here A, B. So A is a matrix representing the left-hand side coefficients of the variables of linear inequality constraints. Then B is a vector representing the right-hand side constants of the linear inequality constraints. Then AEQ. So again, it is a matrix representing the left-hand side coefficients of the variables of linear equality constraints. Then BEQ. So that is a vector representing the right-hand side constants of the linear equality constraints. Then lower bound, upper bound. Then again, M file for the nonlinear inequality constraints. Then options. Only the difference is, so here instead of number of variables, previously we have initial guess. Instead of that, we have to put number of variables, right? So that is the only difference. The remaining sequence is same sequence. So here if you see one problem, colleagues, whether the current file is visible, current word file is visible.
Yes, sir.
Yeah. The same problem, design of open rectangular box, whatever that we have discussed initially, right? So M file for the objective function. M file for the objective function is written. Then again another M file for nonlinear inequality constraints, only one constraint. Then so this one relate to the run file with respect to GA solver. So as usual, so clear all CLs. Then here initial guess need not required, right? Initial guess need not required, that you can delete. So lower bound, upper bound. So then matrix A, then vector B, matrix AUQ, vector BUQ, then options, then X and F val, GA, and then all the input arguments. So M file for @GPP_main, that is M file for the objective function. Then number of variables. Then matrix A already declared, so empty square bracket. Then vector B already declared, right? Then AEQ already declared, PEQ already declared. So since that are not applicable, we have to put empty square bracket on it. Then lower bound, upper bound, then again another constraint that is representing the nonlinear inequality constraint. Then finally options, right? And then to execute the values of the nonlinear inequality constraint, so this we have to type C, CEQ, that M file representing the nonlinear inequality constraints should be recalled here, so that it will be executed, right? So in MATLAB, if you see the same thing. So my dear colleagues, I think the file is visible, MATLAB file, right? So
Yes,
same M file for the M file representing the objective function, and then M file representing the constraints, and then another run file with respect to GA solver, right? So here since GA solver as per the mechanism of genetic algorithm, as sir was discussing morning, so here it takes default values for the initial population size, right? So initial population size, it takes default value. Then length of the chromosome, it takes default value. Then number of iterations, the number of populations, number of generations, it takes default value. Then another one is crossover probability, it takes default value. Then mutation probability also, it takes default value, right? Generally crossover probability is more, then mutation probability is less. So such a way default values it takes, and then the solution can be executed. But however, whether you use so GA user interface in the MATLAB or GA solver, right? So each and every time whenever you run the solution, so slightly with a little bit difference, the solution gets deferred, because every time while generating the initial population, so initial population is generated based on the random numbers. So that is why every time, since the random numbers being generated in the mechanism of the algorithm, so it varies. So that is why every time you will get the different result. But even though the result is different, but that result is not said to be significantly significant. It is not significant difference, right? So statistically, if you perform some t-test or something, so it shows that statistically that difference is insignificant only. So that is why, so people have been using GA solver or GA user interface, right, widely for solving all the research problems. And then after running the program for minimum 20 to 25 times, finally they are performing some t-test, and then they are showing that the result is statistically, difference in result is statistically insignificant. So that way it is also acceptable. So because learning GA mechanism and then again writing code, so is said to be somewhat difficult process. Unless we are very familiar with respect to programming languages, so the GA program cannot be written thoroughly. So that is why, so instead of that, one can go for usage of GA solver or GA user interface, right? So if you run the same file, so this is the output result which we will get. So X values and F values within the given lower bound and upper bound, the optimal values, and then objective function value, and then value of the nonlinear inequality constraint, right? So this is the way how we can write M file for objective function and M file for nonlinear inequality and equality constraints, and then run file to execute the both M files of objective function and constraints, right? So I hope to some little bit extent, I hope, unless otherwise one can practice thoroughly, then only so easily you may get familiarity, and then you won't find any kind of difficulty in writing files for all these objective function constraints and then run file, right? So that if we are familiar once, then we can make use of these solvers to solve our research problems, right? Because since nowadays in each and every organization, the MATLAB has been under widely usage, so that is why MATLAB can be used. So as far as optimization is concerned, so MATLAB usage is said to be more flexible enough for the research perspective.